Okay, let's dive in. In this episode, we will talk about Flow-GRPO, training flow matching models via online RL. We're looking at some really interesting research here, bringing together flow matching models and online reinforcement learning, or RL.
That's right. And flow matching models, they're kind of the state of the art right now for generating images, video too. They have this strong theoretical backing, give you really high quality results, and they're getting faster and faster at sampling. Models like SD 3.5 FLUX, they're built on this.
But they're not perfect, are they? The sources we looked at mentioned they can struggle sometimes, especially with complex stuff like getting the number of objects right or specific spatial relationships, putting things in the right place, and text and images that seems particularly hard.
Exactly. And that's really the motivation here. We've seen online RL do amazing things for large language models, LLMs, right?
Yeah.
Improving reasoning, following constructions. Better think DeepSeek R1 or OpenAI O1. So the idea is, can we use that same kind of feedback loop from online RL to fix these specific problems in flow matching models for images?
It sounds like a great idea, but yeah, there are a couple of big hurdles straight away. The research points out this fundamental conflict. Flow models generate images deterministically, they follow a set path. But online RL, it needs randomness, stochasticity to explore.
That's the first big one. And the second, efficiency. Online RL needs tons of samples to learn, loads of data. Flow models, while maybe fast for one final image, still take quite a few steps. You mentioned maybe 40 for SE 3.5M. Doing that over and over for RL training data gets really, really expensive, computationally speaking.
Okay, so the challenge is clear. Our mission for this deep dive, then, is to explore the two main strategies these researchers developed to make this combo work, and then really dig into why the results, especially for text-to-image or T2I generation, are pretty significant.
Sounds good. Let's get into it.
All right, maybe let's quickly recap the basics. Flow matching models, how should we picture how they work, simply?
Okay, think of it like learning a smooth transformation. You start with pure random noise, like TV static, and the model learns a precise path, a flow, to turn that noise into a coherent image. It learns its velocity field, basically instructions for how to move along that path over time. Mathematically, it's learning to solve an ordinary differential equation, an ODE.
An ODE, got it. And they train it by making sure the predicted velocity matches the true velocity needed at different points.
Pretty much, yeah. And like we said, they're dominant now because they're well-grounded theoretically. The image quality is fantastic, and you can sample deterministically relatively quickly once trained.
But back to those weak spots, complexity, text.
Right, the research really confirms this. Ask for, say, 3 red cubes to the left of a blue sphere. We might get the colors right, but mess up the count or the position. And text, generating readable text within the image. That's notoriously difficult. Often comes out garbled.
Okay, problem defined.
Yeah.
Now, online RL, we know it helps LLMs reason better. What's the magic ingredient there?
It's the interaction. The model, or agent, tries things out in an environment, gets feedback, a reward signal saying good job or try again, and learns from that experience. This constant trial and error, exploring different actions, is super powerful for learning complex behaviors.
And people have tried RL with image models before, but maybe not quite this way.
Yeah, often it was with older diffusion models, or using offline RL methods like DPO, direct preference optimization. DPO learns from a fixed set of examples, like pairs of good and bad images. But online RL, where the model actively generates, gets feedback, updates, generates again, all in a loop. Applying that specifically to flow matching models is relatively new territory.
Which circles back to those two big challenges. First, deterministic flow versus stochastic RL.
It's a core mismatch. The ODE gives you one single path. No probabilities, no exploration space. RL needs that. It needs to calculate the likelihood of taking certain actions to update its policy. You can't do that with a deterministic process.
And challenge number 2, sample generation speed for training.
Right. RL needs potentially thousands of samples just for one update step, running 40-plus denoising steps for each of those samples. Just way too slow for practical training of these big models. They needed a shortcut for training data generation.
Okay, problems established. Enter Flow-GRPO. It uses group relative policy optimization, GRPO. Why that specific RL algorithm?
Well, the paper highlights GRPO as being more memory efficient than something like PPO, proximal policy optimization. PPO often needs a whole separate value network to estimate how good a state is. GRPO avoids that. It compares samples within batch or group against each other to figure out which actions led to better rewards. Less memory overhead.
Makes sense. So GRPO is the RL part. How does Flow-GRPO tackle the two main roadblocks? Let's start with making the deterministic flow stochastic, the OD to SDE conversion.
This is really clever. They realized that the same process transforming noise to data can be described not just by the deterministic ODE, but also by an equivalent stochastic differential equation, an SDE.
Stochastic, so adding noise.
Exactly. It's like taking the original smooth path and adding a little bit of controlled random wiggle at each step. The SDE is constructed mathematically, so that despite the randomness, the overall distribution of where you end up at any point in time matches the ODE. The noise comes from a Wiener process, mathematically speaking.
And they can derive the specific SDE for the flow model they're using.
Yes, for rectified flows, which are common, there's a known link between the learned velocity field and the score function related to the data's probability distribution. Using that link, they can write down the exact SDE equivalent to the model's learned ODE.
Okay, so now you have an SDE. How does that help get random samples for RL?
Well, just like you discretize the ODE to sample, you discretize the SDE. And when you write out the update rule for the SDE steps, it naturally includes a random noise term, usually sampled from a standard Gaussian distribution. This noise injects the randomness you need.
Uh-huh. So every time you run the sampling process, you get a slightly different trajectory because of that random noise.
Precisely. And crucially for RL, the probability of transitioning from one state to the next isn't one anymore. It becomes a probability distribution, a Gaussian, in fact. This means you can actually calculate the probabilities needed for the RL updates, like the KL divergence term in GRPO. And the noise itself provides the exploration RL needs.
And they can tune how much noise, how much exploration?
Yep, there's a parameter in the SDE formulation, let's call it A, or the noise level, that scales the amount of randomness. Tuning that controls the exploration-exploitation trade-off during training.
Okay, ingenious. Solves the stochasticity problem. What about the speed problem, getting samples fast enough? Strategy 2, denoising reduction.
But this is the pragmatic fix, the problem.
Yeah.
40 steps per sample is too slow for training data. The solution, during training only, use way fewer steps, maybe just 10.
But wait, wouldn't 10-step samples be, well, kind of low quality?
They would be, yes, compared to the final 40-step image. But the key insight is that these faster, lower quality samples are still good enough to provide a useful reward signal for the RL training. They carry enough information to tell the model if it's moving in the right direction, reward-wise. Then, crucially, when you're done training and want to generate images for real, you go back to using the full 40 steps.
So fast and maybe rough samples for training, slow and polished samples for inference.
You got it. It speeds up training data collection massively. They show over 4x faster without hurting the final quality of the aligned model.
That seems like a really smart trade-off. So putting it all together, Flow-GRPO takes a prompt, uses the SDE version for stochastic sampling, runs only a few steps, denoising reduction, to get a sample quickly, calculates a reward, and then uses GRPO comparing samples in a group and using that KL penalty to update the model.
That's the loop. Generate stochastically and fast, evaluate, learn via GRPO, repeat.
Okay, let's get to the results. This is where we see if it actually works. 3 T2I tasks. What's the big picture from the experiments?
The big picture is really positive. Flow-GRPO consistently improves the model on the specific task it's trained for, like counting objects correctly or rendering text. And importantly, it does this while maintaining the overall image quality and avoiding serious reward hacking.
Ah, yes, reward hacking, where the model finds a shortcut to get the reward without actually doing what you want. Always a risk with RL. Okay, task 1, compositional generation on the Geneva benchmark. What's that test?
Geneva throws really complex prompts at the model, things about object counts, spatial layouts, specific attributes on specific objects. It uses an automated system to check if the output image matches these instructions accurately.
And the results. You said they were good.
Remarkable, really.
Uh-huh.
The base ST3.5 medium model scored around 63% on Geneva. After Flow-GRPO tuning, it jumped to 95%.
Wow, 95%. How does that compare?
They benchmarked against GPT-4o, a very powerful multimodal model, which got 84% on the same task. So, Flow-GRPO pushed ST3.5M significantly ahead on this specific compositional benchmark. You can see it in the example images getting counts right, left of, behind specific colors on specific objects. The rewards were designed to directly measure this, like comparing generated count to requested count.
That's a huge leap.
Yeah.
Okay, second task, visual text rendering.
Yeah, getting the model to write specific words or characters correctly inside the image. They treat it like an optical character recognition (OCR) task. The reward is based on how accurately an OCR tool reads the text in the generated image.
And the improvement there.
Similar story. SD3 Medium went from about 59% in text accuracy to 92% after Flow-GRPO training. Again, tackling a known weakness head-on and getting major gains.
And the third task was aligning with human preferences.
Right. Here they used a reward model called PickScore, which itself is trained on lots of human choices about which images look better or follow prompts better.
And Flow-GRPO worked for that too.
Yes, it improved alignment according to PickScore. This shows the framework isn't just for objective, rule-based tasks like counting. It's flexible enough to align with more subjective, human-like preference signals as well. It's quite general.
Let's talk about that reward hacking prevention again. How did the KL constraint help maintain quality?
It's vital. That KL term in the GRPO objective basically tells the model, get better at the task, but don't stray too far from how the original pre-trained model behaves. They tested this explicitly. They measured general image quality using standard metrics on a broad benchmark called drawbench.
What happened without the KL constraint?
Well, for the composition and text tasks, if you remove the KL constraint, the task score might go up, but the general image quality metrics on drawbench drop. The images start looking worse overall. And for the human preference task, PickScore, removing KL caused the diversity to collapse. Even with different starting noise, the outputs looked almost identical. The model found a narrow way to maximize the preference score.
So the KL term keeps it grounded.
Exactly. It lets the model improve on the specific task reward while preserving the general quality and diversity learned during pre-training. They mentioned trying other things like combining multiple rewards, but found the KL constraint was the most effective way to get the best of both worlds.
Makes sense. And they did specific tests on the two main strategies too, right? Ablation studies?
They did. For denoising reduction, figure 5A in the paper is pretty clear. Training with 10 steps was over 4 times faster than training with 40 steps for the Genival task. And crucially, the final reward achieved was just as high. Big speed up, no performance loss.
Confirms the efficiency gain. And the noise level A for the SDE. How much exploration is best?
Figure 5B shows that. Too little noise, say at 0.1, and learning is really slow. Not enough exploration. A moderate amount of noise, like a 0.7 in their tests, significantly speeds up how quickly the model improves on the task reward, like OCR accuracy. Better acceleration helps find good solutions faster.
But you can have too much noise.
Apparently, yes. If they cranked it up too high, say a 1.0, it didn't help learning more and started to hurt the quality of the intermediate samples, sometimes making training unstable. Their advice seems to be, use as much noise as you can get away with while keeping the training samples reasonably coherent. Find that sweet spot.
Good practical advice. One last thing on results. Generalization. Did it work on things it wasn't explicitly trained on?
Yes, they checked that too. It generalized well to object classes it hadn't seen during the Flow-GRPO tuning. It also generalized to object counts beyond the training range, like training on prompts with 2-4 objects but testing on 5 or 6. Still performed well. And they tested on a whole different benchmark, T2I comp bench plus D, which uses different kinds of objects and relationships. Flow-GRPO still showed significant improvements there too, so it seems pretty robust.
Sounds very convincing then. A solid method. Did they mention limitations or where this could go next?
The main limitation acknowledged is the current focus purely on text-to-image. The obvious next step is video generation, since flow matching is big there too, but video brings new challenges.
Right, like how do you even define a good video with a reward? Motion, consistency over time.
Exactly. Designing rewards for video is much harder. You need to think about physical plausibility, things moving smoothly, characters staying consistent frame to frame. It's complex.
And you might have multiple goals for video quality, coherence, following the prompt, potentially conflicting goals.
Precisely. Balancing these different reward signals effectively will be key.
Plus, video is just bigger, more data, more computation.
Way more. Scaling this kind of online RL approach to the demands of video generation will definitely require further work on efficiency.
Okay, so wrapping up, Flow-GRPO seems like a successful way to integrate online RL into flow matching. The key tricks were that OD to SDE conversion for stochasticity.
And the denoising reduction for training speed.
And the results show it really boosts performance on tricky T2I tasks, complex compositions, text rendering without wrecking the base model's quality, thanks to that KL constraint.
Yeah, it delivers state-of-the-art results on benchmarks like Genival. It's a really promising step towards aligning these powerful generative models more closely with detailed human instructions and preferences.
It feels like moving beyond just make a pretty picture to make exactly this picture with these details. That level of control is quite something.
It definitely is. And that leads to a final thought for you, the listener. How might this capability, being able to fine-tune these incredibly powerful image generators with precise feedback, change how we use AI creatively? Think about design, art, maybe even scientific visualization. What new doors open up when you can reliably tell an AI to generate complex scenes or data representations with this level of accuracy and control? What possibilities does that unlock?